Let's start the recording. Everybody, hello, welcome to MATH7501 on Tuesday, 5 p.m. in Brisbane, different times elsewhere. We'll do a bit of a questions session. There was a question before that we won't appear in the recording. The next questions will. So who has a question? Please don't do direct, just send to everybody unless, yeah, that's a preferred one. So do you have it? But that's okay, I'll read this one. Do you have any tips on how to start with question 8 and B? Let's look at question 8 on the assignment. So we are here. This is not the right year. This is the right year. Let's go to the assignment. Yeah. Question 8A and B, we're actually just getting to that in the lecture. So hold on tight with the questions, and we're actually, this is exactly where we pause. This is like the moment of truth. Okay, so we'll get to that. So 8 we'll get to. Other questions? Okay, I see a relief. Good.
May I ask a question?
Of course.
For question 2, part B, are we going to prove the equation that you put in?
For question which number, please?
2, part B.
Oh, 2. Okay.
Yes.
Yes.
The sum.
Yes. Yeah. So prove it in one of a zillion ways. Okay. So many ways to prove this.
Yeah, because there is a common way, famous way for prove it. Can we use that, or
yeah,
we should
sure.
example?
So in this case, you can look it up if you don't know. So there's a way by writing twice the sum and then flipping the order and adding up. But you can also do a geometric proof if you just look at a cube and you go, you know, this is like the number of elements in an upper triangular matrix, and you just add them up. There's all kinds of ways. Okay, so actually let me give insight on that. So let's say, assuming somebody has not seen kind of one of the standard proofs, then this number, let's relate it to something else. When you're looking at an upper triangular matrix or a lower triangular matrix, and I'm talking about an n by n matrix. Okay, so let me see if I can actually annotate on the screen here. You can see my annotations, right? So this is like a matrix. Let's do a 4 by 4 matrix. Okay. So one way is to take what I'm doing now and formalize it into a proof, but you don't have to do exactly what I'm doing. Okay, so if this matrix is upper triangular, similarly, it could have been lower triangular, I'm going to color all of the entries where we know we potentially have non-zero numbers, right? The data used in an upper triangular matrix is not n squared, right? The data used in an upper triangular matrix is less than n squared. Do you agree? I mean, if I give you an n by n matrix in general, in this case, n equals 4, the data would be n squared. But in this matrix, well, we don't have 16 data points. We actually have 1 plus 2, which is 3, plus 3, which is 6, plus 4, which is 10 data points, right? Now, if you plug in this example, this is exactly what you get. You get 10 data points. Now you can see here that that if you'd want to compute these data points, one way to do it is to say it's roughly half of n squared, but it's not exactly half of n squared because you also have the diagonal, and that would give you this formula. Okay, whereas the formula on the left is actually you're summing, right? This, say, and this, and this, and this. Exactly, it's 1 plus 2 plus 3 plus 4. So that's probably not the standard way you're referring to in your question, but that's a way that at least connects it to matrices. So anything goes. Okay, did that help?
Thank you.
No worries. More questions?
Excuse me?
Oh, yeah, after you. Yeah.
Okay, at first, and when we need to use Mathematica in this assignment, do we need to put the code and the screenshots in the PDF or only the code?
But both. So please format according to, let me clear this drawing, and get out of this. Thanks for asking. So you got your instructions here. Submit a single PDF, do not submit the code files, but instead format your code into a PDF file. Now, when we're saying the code, it's the code and the output. Okay, it doesn't have to be production quality. So you can do it with screenshots, but make sure the screenshots are not extremely ugly pixels. So kind of slightly more better screenshots, and just format it into one document in Microsoft Word or in any other mechanism you see fit.
Okay, thank you.
Okay.
Sorry. About the formula simplify problem. For example, the 2D, do we have to simplify the formula until we can't simplify anymore? Or
yeah, I mean, in general, in mathematics, you want to simplify it into, sometimes there's not a unique, most simplified expression, but you want to do it for that.
okay, thank you.
Okay. I got a private question about I'll answer the privates just in the break. That's specific, just because to focus on all, but it's in the queue. Remind me if I don't get to it. Are there more questions about the assignment? Okay, more questions about the assignments? Okay, come on, let's get to it. We were just, I think, in like one of the nicest things one can do. Well, or maybe not, but we're doing something. We're doing combinatorics. And let's remember where we were, and that will relate to your question 8. Sorry. Okay, so these are all the scribbles from last week, and we'll reconstruct this this table we got to. This one. Okay. A lot of scratches here, so I'm actually going to start and just draw it again to review, but I just want you to see it. So this is, oops, sorry, that's not what I meant to do. This is where we stopped. This is where we roughly stopped, but you have this as kind of unanswered. So let's do that. But I'm actually just, because there's all this bug in the software, I'm just going to start and make a new note. Before I was scratching together with the other lecture note. So the story again, I'm just reviewing quickly. Balls into bins. How many balls did we have in terms of letters? 2 balls. Well, or in general, in terms of letters, I think we had, what were the letters? Just checking that you're, yep, K balls into N bins, right? Okay, so we had, I hope I'm keeping this in the same order. So K balls and N bins, okay? N bins. So the balls could be indistinguishable. So they're the same balls, same looking. Okay, I'm writing that because I don't know how to spell indistinguishable. Or they can be unique. Okay, so balls with numbers, right? And the bins could have a limit of 1 or unlimited. Limit of 1 ball or unlimited number of balls, right? That's the story. So we took our time through this. This is just a quick review. So we said, well, if the ball, I'm just going to go through it very quickly. So if the balls are unique and there's unlimited balls, so you can put the first ball in N bins, second one in N bins, third one in N bins, the fourth one in N bins. So you've got N times N times N times N, K times. Okay, please stop me if I make a mistake. And if the balls were now I'll go, and then we went our arguments were here, and we said, well, if now there's a limit of 1 ball per bin, right? That's what we're doing, a limit of 1 ball per bin. Then what we're doing is, I'll write it like this, nk over k times k factorial. And this is not the way we would have introduced it first, but now you know, we also spoke about nk over k, the binomial coefficients, right? which is this. And this is just n times n minus 1 times n minus 2 times n minus k plus 1. Okay. And what is this thing if k equals n? What is this thing if k equals n? What is this thing if k equals n? It's no, not exactly 1. So if k equals n, there's n balls and n bins. And the balls are unique, and there's a limit of 1 per ball. If k equals n, what formula is going to be this? Okay, now I'm seeing some good answers. So this is n factorial if k equals n. Okay, if k equals n, it's n factorial, because that's a number of permutation. Of course, you can just see this, right? So you put here n, so n on n, which is like n on 0, is 1. Okay, all right. Just to get our head straight. Okay, good. So let's undo some scribbles. Oh, I don't know. We'll delete this. Oh, kill too many things. But let's n over k. Now, if the balls, then kind of we went after, you know, then we went from this to this. Then we said, well, let's go from this to this. And again, we didn't write it like that. We wrote it like this. But this is now just algebra, the relation between these two things. And then we went up to the case where the balls are the same looking. So you can distinguish between the two balls or the k balls. And there's a limit of 1 ball per bin. And that's exactly, this is kind of the, in many ways, the most common case. This is the number of subsets you can sample from a set. The number of subsets of size k you can sample from a set of size n. We'll speak about sampling in a second. Okay, we'll relate this to a sampling problem. Okay, those of you that are doing data 7001 are also doing sampling. Okay, so it's at least it's enumerating sampling. And here we just had n over k, n on k, n choose k. Okay, again, in other places you might see that people would write this as c n k, and this people write as p n k, but we're not going to use these really. Okay, which one is bigger for any fixed n and k? The yellow, the top one, or the blue one? Which one is a bigger number? The yellow? No, not the yellow, the blue, right? I mean, because then the balls are unique. So for every setting above, you have k settings below because you have a permutation of the k balls. Okay. So now we've just limited to the last case, which is slightly harder. Well, but it's not rocket science. We can do it. We can do it. It's going to happen. Okay. And in this case, we have configurations such as, look, here I'm going to put a ball. Let me put some bins for a bit. 1, 2, 3, 4, say bins. And I'll put like 2 balls. Okay. Now this is like one configuration in the above. All right. This is like one configuration in that. Okay. This is, I'm drawing this for n equals 4, k equals 2. But of course, there's others, right? I can take this ball here and move it here. That's a different configuration, or I can move it here. But the thing is, I can even move it here. That's also a valid configuration, right? I mean, all these are valid configurations. So we've got all these valid configurations. Okay. So the question is, how do we count this? So for this, let's do a bit of a trick. So instead of representing the configuration as I did now, balls and bins, right? And you see what I mean? The configuration I could have also taken here. I could have put these guys here, could have put them here, could have put them here, I could have put them separate, etc. What I'm going to do, this is maybe in slang calls it the balls and separators trick. Okay. The balls and separators trick, what I'm going to do is I'm going to call this is a separator because it separates 2 bins. This is a separator because it separates 2 bins. Separator, like separation. See my, Okay, is separate, and this is a separator. It separates two bins. Now, I'm not going to consider these edges here because well, you'll see in a second. Now, look, I'm now going to draw some configurations of balls and separators. Look, I'm going to do ball, separator, 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 ball. Okay, so look at this thing that I'm highlighting now. Just take a bit of a guess. How do you think that describes a placement of balls into bins? What does it mean? I mean, I've just shown you that these are the separators. These are the balls. So what do I mean by this thing? What do I mean by it? In terms of one way of putting same looking balls with unlimited numbers into bins. What do I mean by this? What do I mean? Well, I mean that there's a ball here, and there's nothing here, and a ball here. Okay, let me do something else. Let me do ball, ball, separator, separator, separator. What do I mean now? So let's try to. I mean, it's hard to answer. It's hard to answer what I mean like by words, but maybe you can. So, oh no, it's easy. Of course, you've shown me that it's easy. Why is it hard? Very good. You said both in the same bin. So this guy here, this this blue configuration here, that maps to ball here and ball here, right? And then you got separator, separator, separator. Let's do a different one. Let's do separator, ball, separator, ball, separator. Okay. What does that mean? What does that mean here? What is this red? Let's not do red. Let's do, what does this configuration mean now? It means a ball's in the second bin, just like you're saying. Very good. So I'll delete the balls. It means a ball's in the second bin, right? And a ball's in the third bin. Now, have I convinced you that for any way in which you can place same looking balls into bins with an unlimited number, you can, instead of doing this, you can encode it, you can represent it like one of these ways, right? And for every one of these ways, there's exactly a way of separating balls into bins. There's just a comment, we can change the ball and separator position, right? So basically, and everything's allowed, right? Like you can do like separator, 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 ball, ball. That means something, right? Now it's clear to you, right? The two balls are here. You can do everything in the fourth bin, exactly. You can do separator, ball, ball, separator, separator. You can do separator, separator, ball, ball, separator. These are not ones, they're separators. That's pretty good. Okay, so how many separators do we have? 3. And if we're kind of speaking with our n bins, how many separators do we have? N minus 1. So what we've got is n minus 1 separators. How many balls do we have? K. We've got K balls. Now the point is, we could speak now about not balls into bins, but an arrangement. So let's call this total, let's call it characters, equals n minus 1 plus k, right? Because each one of these representations, look, it had 1, 2, 3, 4, 5 characters. 1, 2, 3, 4, 5. It had the n minus 1 separators plus a call. So that's the total characters. So what we need to do now is we need to choose out of these total characters which ones are going to be separators and which ones are going to be balls. Where in this matrix is this answer kind of answered before? Okay, so it's like you could have had n minus 1 new bins, and these new bins are those characters, and sorry, n minus 1 plus k new bins, right? In our case, it was 5 in this example, but in general, it's n minus 1 plus k. And you need to choose which ones of these are going to be balls. So it's as though you're putting the ball characters in n minus 1 plus k bins. So does anybody have an answer? Which one? What's going to be the formula? Can anybody give me a formula here? First column. Oh, A11. That's the one we use. Okay, so it's going to be something like this. It's going to be out of n minus 1 plus k. How many do we need to choose? Okay. Exactly. That's it. So your reasoning went from here to here, from here to here, from here to here. And now you've got all 4 cases. Okay. Let's just see for this example that we have. So in our numerically, I mean, in our example, we had n equals 4 and k equals 2. So, and let's do all the cases actually. Let's just do all the cases. So here we've got 4 to the power 2. That's, I believe, 16, right? Here we've got 4 on 2, which is 4 factorial divided by 2 factorial, 2 factorial, which is 6. Here we've got 4 on 2, which is just like before, times 2 factorial, and that's 12. And here we've got 4 minus 1 plus 2 over 2, which in my book, let's see, 4 minus 1 is 3 plus 2. So that's 5 on 2. That's 5 factorial divided by 3 factorial, 2 factorial. And that's 5 times 4 divided by 2, or 10. Okay, so 10. I'm a bit quick, but that's okay. That's, I think these are. You got 10 on this bit, 6 on this one, 12 on this one, 16 on this one. Correct me if I made a mistake. I mean, this table here is organized just like this. Okay, so now if you go back to question 8, question 8 asks something different. It asks, you have now n variables, variables, I mean, and k things on the right-hand side, balls. I didn't say that. Okay, so how can you describe integer solutions of non-negative integers of this equation? Yeah, this, I can't scribble on this now, but on this equation, via what we just did. Okay. Oh, well, I mean, argue. So it's an arguing. And yeah, that's it. Questions? All right. So that was the heart of the combinatoric story, of the enumeration story. Now there's a question. So k equals 0 is an abstract k equals 0 is an abstract concept in this context. Yes. Mm-hmm. Yeah. Yeah. Non-negative. I'm going to your question. So k needs to be greater than 1. Greater or equal than 1. K cannot be 0. We should have said this actually. So then it says, yeah. So I'm sorry. This should have said k is a is greater or equal than 1. Oh, this formula might hold with 0. I guess you're right. Let's see. So let's see it with 0. You're right. You're right. I get the answer. Okay, so there's good discussion. But yeah, it also holds with 0. Yeah. Okay. All right. I think we're okay. Let's get back to here. Just a bit more on the notes. Now, there's one formula that I do want to discuss, and that's Pascal's formula. Okay, this is one of those things that it's an identity between binomial coefficients. Okay, now let me suggest for you as quiz practice at home. Well, you are at home. Is anybody on the train or something? Okay. So as quiz practice, prove algebraically. What do I mean by prove algebraically? Right, n plus 1 factorial divided by n plus 1 minus r factorial multiplied by r factorial. That's this thing, okay? Then write equals n factorial divided by n minus r plus 1, right? Because I'm doing that factorial times r minus 1 factorial plus n factorial n minus r factorial, and show that the left-hand side equals the right-hand side. You guys remember how to add fractions, a common denominator. Okay. There's a question about the quiz. Yeah, I'll speak about the quiz as well. Okay, so this is prove algebraically. Okay, and then if you do that, that'll be a proof of this formula, which is sometimes called Pascal's formula. Anybody ever program in the language Pascal? You guys are too young. Oh, you did. Okay. In school. All right, cool. All right. All capital letters or something like that, I think. Yeah, it was a thing at the time. Then C took over. Okay, so but let's look at this formula not from an algebraic proof, which you should do yourself, but rather just let's look at it from a combinatorial proof, okay? Or which is also, let's understand immediately why it happens. So let's think we have a team, a football team. Now the word football means different things in different places, so let's use the unambiguous word of a soccer team. Soccer team. So it has n players plus a goalkeeper. Okay, so in total there are n plus 1 players. So these guys are standing, the n plus 1 players here. The players are standing, the n plus 1 players. This is n of them. Goalkeeper is slightly different in color. That's a goalkeeper. Okay, that's a 1, and these are the n. And that's the n. So in total, there's n plus 1 players. And we come and we say, hey, we want to choose a subset of size r. So we say, hey, out of these, we choose r. Okay, so from the n plus 1, we choose a subset of size r. Now, if you grab a subset, you can tell me, you'll have subsets that have the goalkeeper and subsets that don't have the goalkeeper, right? So if this was the set of all subsets of size r, you have with goalkeeper and without goalkeeper, right? So I'm gonna, like, each point here is a different subset. These are subsets with the goalkeeper and subsets without the goalkeeper. Let's just do them right. Okay, subsets without the goalkeeper. So you can say the total number of subsets, which is a total number which you have here, are going to be the subsets with the goalkeeper, which is this, plus the subsets without the goalkeeper. Now, why? This is the subsets with the goalkeeper. They already have the goalkeeper, right? So how many subsets are there with the goalkeeper? Well, the size of the sets, because they have the goalkeeper, is going to be r minus 1, because the goalkeeper already took one position, right? So these are the subsets with the goalkeeper. That's this. And these are the numbers which we have here. That's the number of subsets without the goalkeeper, because, you know, we already say that's a subset that doesn't have goalkeeper. So, you know, that one which we have here is not here. It's not a +1. It's not there. That's a subset without the goalkeeper, and we need to choose a subset of size r. So that's a combinatorial proof, which is just as valid as this algebraic proof that I'm asking you to do yourself, just to get a bit more algebra practice. Yeah, questions about that? Both are disjoint. You shouldn't say both are disjoint, just say, are they disjoint? Yeah, they are disjoint, because if a subset has a goalkeeper, it does not have the, it does not have the goalkeeper, and vice versa. All right, let's move on. Now, the notion of cardinality is the size of a set. Now, I must say, there's a few things today. We're actually going to move in through quite a lot of material. I'll send an email, well, a message later that will narrow you down for the quiz, okay? And the algorithm for the quiz should be, first step of the algorithm, do the homework, okay? Second step of the algorithm, follow the information sent and study more. All right. So what I'm going to say, I'm going to go through a lot of material, so apologies, and it's just we'll go what we go, we see what we see. All right. So a set is finite if you can count the elements 1 to n. Okay. Now you can say if there's a bijection between the set and the numbers 1 to n. We didn't speak about bijections yet. We will soon. Okay. We actually just did a bijection here. A bijection is like a mapping between that. Well, it's a function that's 1 to 1 and onto, but we'll speak about it soon. But we actually did a bijection, sorry, not here. This thing called a bijection. Here, what we did was a bijection. We did a bijection between a way of throwing balls into bins and an organization of characters of balls and separators, okay? There was a bijection because for everything here, there was something here, and for everything here, there was a unique something here, okay? So a set is, that's all, that's a basic way to say it at first. So a set is a bijection if you can just number if set is finite, if you can just number the elements 1 to n, and n is a finite number. Maybe a million, maybe a zillion, but it's finite. Okay. Hold on, question. Oh, could you show one example of expanding the factorial? Yes, sure, no problem. Like you're talking about one of those? We can do that. Let's do one of those just a bit slower. 6 on 1 plus 6 on 2. Here's a 6 on 1 plus 6 on 2. Okay. Oh, now this was something we could do using Pascal. So we'll do using Pascal in a second, but let's just do manually. The word manually, like by hand. Okay. So what's 6 on 1? So and manually we'll do two ways. We'll do kind of the easy way and the hard way. So first of all, just what's 6 on 1? Don't even do calculations. Just tell me what 6 on 1 is. 6. Okay. So always n over 1, which is like n over n minus 1 equals n, right? So the number of subsets of size 1, the number of singletons in a set of size n is n. Okay. So you could have just told me that's 6. Like you said. Thank you. Okay, so that's this one is 6. 6 on 2, we actually need to write. So I'm going to write 6 factorial if I want to do that, and then I'll do 6 minus 2 factorial is 2 factorial. And then the thing to keep in mind is always when this number here is small or very large in comparison to this, when it's close to the edges, then a lot of cancellations are going to happen. So this thing is going to be 4 factorial, but this 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And this 4 factorial is, of course, 4 times 3 times 2 times 1. So what I'm marking here in red, this is going to cancel this, for example. Okay, so what we're left with is equals. So the 6 we had before, that's the 6, okay, plus 6 times 5 over 2 factorial. 2 factorial is 2. Okay, and that's 21, I believe. Okay, because that was 15. All right, so that was one way of doing it. Well, I said here another way. Well, instead of this 6, just do 6 over 1 and use the formula, and you'll see that it's 6. But now, how do we do this using Pascal? How do we do this using Pascal? So remind you, Pascal was n plus 1 over r. Yeah, the team and the goalie was the team without the goalie, and the team with the goalie and without the goalie, right? That was Pascal. So what numbers are you going to choose for n and r to obtain this? So n should be, I think, should be what? 6. Okay, so we can put that like 6 plus 6. And here, let's choose r to be 2. So 2 and 1, because this one is a 2 minus 1. Okay, 2 minus 1. And according to Pascal's formula, that should be 7 over 2. Okay, 7 over 2. Now, let's see that this 7 over 2 is indeed this 21, which we get. So 7 over 2 is 7 factorial divided by 5 factorial times 2 factorial, which is 7 times 6 divided by 2, which is 7 times 3, which is 21, and that's what we got. Okay. All right. So that was a bit of that. Okay. All right. So sorry, I started, then I stopped. Now I get back to this. Cardinality. All right. Completely different. Okay. Oh, well, sort of completely different, not really. So I'm saying the word cardinality is a number of elements in a set. Okay. And you could speak about cardinality. We already said if A is a set, this is what you mean by the cardinality of A. Okay. We already spoke about the sign that is kind of heavily overloaded. If A is a matrix, it means determinant. If A is a number, it means its absolute value. If A is a complex number, it means its magnitude, etc. Okay. Now, a set is infinite if it's is not finite, basically. Okay. So, can you give me just in words an infinite set? I mean, all these things we did here, all this counting stuff, everything doesn't work for infinite sets. Real numbers is infinite, natural numbers, etc. Okay. And that's if a set of is infinite. Now, the thing that happens is a complex number is also infinite, etc. Okay. So the thing is, we're not going to get too much time to speak about it. When we speak about infinite sets, it happens that we can also speak about the cardinality. And the way to do this is always to kind of look at two infinite sets and say, oh, that's the way it's been defined, and it works well for math. And we'll say they have the same cardinality if you have a one-to-one correspondence or a bijection between the two sets. Okay, so the sets A and B have the same cardinality if you have a one-to-one correspondence. Let me show you an example. So let's take A, the set of even numbers. Let's take B to be the set of odd numbers. You agree they're both infinite? You cannot, if you were to should tell me, yeah, if they're finite, that means there's only n of them, but then I'll take the next one, and it's wrong. Okay, so how can I make a one-to-one mapping? So what I can make is I can say, well, for every even, so every even is of the form 2k. Okay, so the set A, let me actually just write what the set of even numbers is. A is all of the 2k such that k is an integer. Okay, that's a set of even numbers. And the odds B, I can write that as 2k plus 1, where k is an integer. Okay, so that's a way to describe the evens and the odds. Okay, so what would be a mapping between the two? Right, now somebody tells me 2k minus 1. Yeah, I could have said 2k minus 1. I could have also had 2k minus 25, as long as this is, I fully agree, fully agree. And that's kind of one way to. Okay, so what would be a mapping between the set A and the set B? If I give you an even number, well, maybe just add one to it, you'll get an odd, right? It's kind of looking at the house across the street, okay? In streets where you have evens and odds. Okay, so the mapping will be for every even, just add one, you get the odd. For every odd, subtract one, you get the even. Okay, yeah. Now somebody wrote B equals A plus 1. I mean, yeah, but that's, we need to describe what we mean when we do plus on a set, but in a way, that's the correct one. Okay, so even though these sets are infinite, the cardinality of the evens and the odds is the same. Okay, all right. Now let's go one step beyond. Let's take A to be the natural numbers, which I forgot what we agreed on, but let's just call them 1, 2, 3, 4. Okay, let's do a 0 as well. 0, 1, 2, 3, 4, 5 forever. And let's take B to be the integers. Negative, well, how do I write the integers? I write dot, 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 negative 2, negative 1, 0, 1, 2. Okay. Of which there's more. Of which there's more. More N or more Z? More B. Okay, so you think there's more B because it covers more. However, within this lens that mathematics has chosen of cardinality, there's actually the same number. Well, it's not the same number, it's the same cardinality. Okay, so you can map this to this and vice versa. You can do that. Can somebody give me a way of mapping all of the integers to the natural numbers? In many ways. So one way I can do this, yeah, that's what Jared wrote. Plus minus n looks like a sensible way. So look, I'm going to take here the number line. This is a 0, and this is, I'll draw it like this. Right now, describing it in a nice mathematical way is one thing, but let's just first, I'm just going to write now, I'm going to enumerate. Well, absolute value is not enough because it's not a one-to-one mapping. Okay, so absolute value will bring you from here to here, but it won't bring me back. We'll speak about functions soon and we'll see. Okay, but what I could say that these are now what you see here on this number line, that's all of the integers. Okay, so I'm going to say this is a 0th integer. This is the first one. This is the second one. This is the third one. This is the fourth one. This is the fifth one. This is the sixth one. The seventh one, eighth one, 9th one, 10th one, 11th one. You get where this is going. And I continue this forever. Okay, so if I give you the number, the even numbers, they happen to be negative, and the odd numbers happen to be odd, the positives. Okay, and the zero is even, but we're talking about the, is here. And that's a way of enumerating the integers, and that tells us that you can get from the integers to the natural numbers, and from the natural numbers I can also get to the integers by counting this backwards. And you can even write a formula for this. Okay, you can try it yourself. So that tells us that according to this notion of same cardinality, well, these two sets, even though it might annoy you at first, are the same. It might annoy you because you felt there's more of these, but they're the same. Okay, so these two infinite sets have the same cardinality. Now, why do you care about this as data scientists? I mean, come on, all the data you're going to get, you're going to work with big data, a lot of data, but it's going to be finite. Okay, I mean, you're not going to get, well, infinite data. But it turns out that mathematically, you actually want to think about the cardinality of things, because sets that have the same cardinality of the natural numbers are called countable. Okay, so countable sets. A set is countable if it has, sorry, let's do, if it is finite and or it has the same cardinality as the natural numbers. Okay, so countable sets are important because when you do summations later on, and that's what you're going to start in 2 weeks with Tim, when Tim takes over, you'll do series where you'll have like I is, say, 0 to infinity of some AI. This is what you're going to call a series. But alternatively, you might just want to sum over all of the elements that you can enumerate. So you might want to say just all of the elements, well, I and some index set in some set of AI, and that would mean the same. And you could only give this meaning when the set is countable. So it's kind of getting a bit much, but basically what I'm saying is, okay, the integers and the natural numbers and the evens and the odds are all countable. You can do summations over them. The rational numbers, what do you think? Are they countable? Can you, I mean, it seems like you have many more. They're very dense. Are they countable or not? Take a wild guess. I mean, it's break time anyway in a sec. Rational numbers, are they countable? It feels like no, because they're more, right? They're kind of dense, etc. There's, you get so many rationals. I mean, you've got so many rationals between 0 and 1. But however, because an irrational number is like m divided by n, you can take your m and you can take n and you can kind of count like this, do some configurations like that, and show that they're countable. Okay, so we'll take the break in a second. So so if they're countable, why are we even speaking about it? If everything's countable, why are we speaking about it? So what would not be countable? Take a bit of a guess. What set of numbers is not countable? Complex is true, but even go a bit less complicated than complex. One level beyond the Q, one level beyond the rationals. These are the rationals. One level beyond. What set of numbers is not countable? Well, what's the one set of numbers that slightly extends the rationals? The irrationals, it complements, but we want this. That's true. The irrationals are uncountable, but also the reals. These are uncountable. And we'll speak about the gist of the proof of that just after the break. Okay, so and this kind of has to, it looks a bit philosophical. The person who came up with this is Cantor. Okay, and you can look here, but it's not, it's actually important for data scientists. So you can look here in I'm here in this videos that some of you have been watching. You can look, for example, at this video, which I recommend, on different types of infinities. Okay. Okay, any question before the break? All right, so let's take a 5-minute break, then I'll come back and I'll tend to a few of the specific questions, including I had one on the chat. So see you in 5 minutes. All right, I'm back. I see that the top of my head isn't back, but I'm back. Oh, thanks. Okay, so I'm going to start to get to some. This is still the breaks. Just getting to a few direct questions. Yeah. So Jared, your question is fine. Yes, that's fine. Now there's another direct question I got, but I'll read it. It's a good question, or at least it's valid for everybody. As for assignment 1, could I write the title of every question in mathematics, and in Mathematica, I guess you mean, and save as PDF? Yes, you can. You can even, if you really wanted to, you could format the whole assignment in Mathematica. Okay. Next question. I'm a little bit confused about same cardinality. Set A and B has same cardinality means the elements in the set A have 1.1 elements set of set B, or part of the elements of set A. It means that you can find a one-to-one correspondence between every element in A and every element in B. Okay. So it means that you could put those elements and make some mappings between them. In the language of functions, which we'll get to soon, it means that you have a bijection, which is a one-to-one onto function between the two sets. Okay, but we'll get to that, to the language of functions. Louis, could you help me with the code? Yes, we'll get to that in a second. Do we need reference code that do we need to reference code that we got in the tutorial? No. And the question about referencing code got in the tutorial? No. Okay, let's just look at Louis's question a second. It might extend the break just a bit, but that's okay. It's an active break. What do? I go to here and stop the share. And share screen here. And that's not what we want. So, sorry a second, just a bit lost. Lewis's code. Lewis's code. Where are you? Lewis's code. Go to the chat. Okay. I'm just gonna key in some variant of this, okay? So the function transpose, I'll do it quickly. So trans AB, which gets a size and a range and an n run, and that's a module, and it has A and B and n, which is the size. Oops, that's not where I wanted to type. Which is a size, and R, which is a range, and count, which is 0, and F, which counts false equals 0, and R run, which is n run. Yeah, there wasn't a need to create all those local variables, but why not? Okay, let's just first make this 22, okay? So it'll just return 22. So if I drew trans, just to see what this does. So trans AB on size 3, 100,000. I'm starting to see what you have in the code here. I think you put here 100, like that, maybe. Look, and it's could this 100,000 here No, that's wrong. Okay. I mean, I'm wrong about that. That's just 100,000. Okay, so that returns 22. Now, A equals. Oh, okay. I see your problem, Louis. Sorry. So you see this thing is blue, rand M. Yeah.
Yes.
You didn't run it. You didn't run rand M. So you see, Mathematica, unlike Python or R, you can use stuff that you haven't run, and it won't yell an error because rand n is a symbol. You see, so look, I just showed here. I'll do A is my rand M. Such a thing doesn't exist, NR, right? But I ran it. Everybody's happy. Too happy. Okay, like happy and comfortable. You know, like humanity with global warming, just thinking it's all good, but maybe it's not. Okay, and then here the other thing, B. Also, we're happy. Right, and now I can do, look, I can do A dot B. I don't know how I'm going to do this nice transpose. What do I do? Control T, Command. Not sure how to do this transpose. But transpose, maybe I'll just do like that. Equals transpose A dot transpose B. I'm going to get a false. Well, I'm going to get a, I'm going to get this thing, which is neither true, just false. It's just an equation. So then if I'll do an if on that, and if takes the second argument as a true thing, right? So I'll take print true and then print false. What is it printed? Well, it didn't do anything. So the thing, I guess the way if works is if the condition doesn't evaluate to neither true or false, it just keeps it as an if. So this thing does neither of these two things run. Okay, you see, if has a third thing, if condition is neither true or false. Now in other languages, condition won't be either true or false because something has to evaluate it true or false. But this thing is neither true or false, so it kept it symbolic. Basically, you didn't run these two things. Got it?
Okay. See, if in this case, how can we fix these issues then?
Run random. Create random prior. The function random is not defined. That's Amina's function. So up in the GitHub above that, she will have random, right? So just run that and that should work.
Oh, okay, I see it now.
Yeah, subtle point, subtle issue. I mean, I didn't see it on the first look, but okay, good you asked. More questions? All right, let's officially finish the break. When the break is officially finished, let's get back to class. Sorry, it took a while, but hope this was of some use. And let's share this iPad. I must say I'm feeling not too good. So if I suddenly collapse, then maybe I'm just going to croak during the lecture. So somebody please upload this lecture to YouTube for me because it will be very popular. Lecture has a heart attack during lecture, not feeling great. But I don't think that would really happen. Just in case, let's still make sure to upload it. You need to ask my partner to upload it for me. Okay, it's saved onto the cloud. All right. So I'm gonna skip this stuff because all I wanted to do is speak to you just a bit about countable and things like that. But I stopped before and I said the set R is uncountable, and the point to that is I'll only sketch the idea because it's a bit of an idea one can speak about for a long time. So instead of speaking about the set R, let's just call it the set 0, 1 is all of the x's in R such that x is in 0, 1. Okay, the interval of numbers between 0 and 1. So let's call this A. Okay, so that's the interval. This is 0, this is 1 on the number line. It's everything here. And somehow this mathematically, in mathematics, it's not countable. So a way to do this is not to speak about this specific set, but actually speak about a different set. And let's call this the set B, which is the set of all sequences. Let's just write it in words. All infinite sequences, all infinite binary sequences. Example 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 1, ta 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 forever, or 1, 1, 0, 1, 1. I'm just putting random numbers, 0, 1, 1, 1 forever. Okay, so call the set B of all infinite binary sequences. Now the set B is almost the set A because any number here you can represent using binary notation, right? So with binary numbers, you can do it as like decimal binary numbers, you know, where the weight of this is 1/2. Let me do it in a different color. 1/2, and the weight of this is 1/4, and the weight of this is 1/8, and the weight of this is 1/16, etc., etc. I mean, there are some issues with repeating numbers and things like that, with if like it's all ones or all zeros, but let's leave that. Okay, so Cantor's theorem back in the 19th century that shocked mathematics, and he's the father of set theory, etc., and things like that, was that this set B is not countable. So, you know, some sets are countable. We showed, well, I didn't show you exactly Q countable, but we showed you that the evens are countable, the odds are countable, the natural numbers are naturally countable, the integers are countable, but some sets are not countable. And this set of all infinite sequences is not countable, which maps to the set A. And from this, well, A is a subset of R, right? Because R is many A's, so R is also uncountable. And that kind of introduced the whole notion of cardinality. So that means there's different cardinalities of sets in the infinite world of sets. So the proof went roughly along these lines. So I'm just going to say it verbally. Okay, this is not formally. So assume, and this is proof by negation, assume B, so proof, is countable. What does that mean? It means you can enumerate the elements in B. So enumerate its elements. How do you enumerate the elements? You can say, here's the first one. The first one is maybe 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, etc., whatever. And there's going to be the second one, you know, 0, 1, 0, 1, 1, 1, 0, etc., forever. Of course, we don't know what the enumeration is, but if it's countable, there exists some enumeration where you enumerate them one after another. You know, there's going to be the third one, 0, 0, 1, 0, 1, 1, etc. We don't know exactly what an enumeration, but there would be an enumeration. Okay. Now, take an element U, which I'm just going to draw, which is going to have, look at this diagonal. It's going to look at the diagonals here. Which flips every bit in the diagonal. So what do I mean? So if you gave me an enumeration, I'm now, here's enumeration, here's the enumeration. Okay. And what I'm going to do is if something was a 0, I'll make it a 1. And if it was a 1, I'll make it a 0. And if it was a 1 here, I'll make it a 0, etc., etc. So I'm going to flip everyone. So this is this new element, U. Now, U, this thing, is also an element of B, right? Because it's an infinite sequence. But it's not the first element, and it's not the second element, and it's not the third element, because it differs from each of them. And it's not the fourth element, and it's not the fifth element, and it's not the sixth, and it's none of them. So that means that there's no way in the world that we can enumerate. That's a proof. That's all. And that means that B is not countable. This thing drove mathematicians crazy for many years. But finally, there's an agreement that there are sets that are non-countable. And that's the crux of the proof that the reals are not countable. Okay. Questions? You're shocked. I mean, so was the mathematical community of the 19th century. Okay. We're moving on to the next unit, Foundations in Logic. Before we do that, and let me actually remember the time now, it's now 6:15 in my time. I'll do what I promised. Speak about the quiz a bit more. Okay. So if we go to all right. So I wrote you a big love letter here. And that's this towards quiz 1. So much information, because all these questions are always asked. But this is simply how it happens. So read this email quite carefully, please. Next couple of days, you're going to write a 1-page formula sheet. Yeah, not 2 pages, 1 page. So this formula sheet will have a summary of the key results, definitions, whatever you want. You can write quite small if you want, etc. You'll prepare it. You can type it, and you prepare it. Can you use Apple Pencil? Yes, you can. Okay, so you'll write a 1-page formula sheet. And then when you do the quiz, you'll have the formula sheets, but you will not use any material from the internet. You will not use a course website. You will not use files from the computer. You won't use any written notes. Basically, you just have the formula sheet and a scientific calculator. And if you don't have a hard calculator, you can use your phone calculator. That's fine. Okay, phone, scientific calculator, scientific mode, etc. That's fine. But then when you come to the quiz, you sit the quiz. First 10 minutes is what's called reading time. That's, by the way, in any UQ exam. Okay, so the way that works, the reading time, is you look at the questions. You can start to work if you want, but it's important that you actually take the time to read all the questions and see that you understand the questions and the notation. And then you could put questions in the chat to me during the reading time, okay? And I will answer. But the questions have to be, hey, I don't understand what this says. I'm not going to answer helping with the quiz, right? So I don't understand this. I don't understand that. That's at the end of the reading time. At which point you go on with your quiz. So you have a total of 10 minutes reading time and 60 minutes for the quiz and 20 additional minutes. So it's total 90 minutes. So 20 additional is for taking photos and creating a nice PDF document. You need to make sure you're practiced for that, right? So photos, scanning, etc. The PDF document for uploading your quiz. And you also need to take another minute or 2 or 3 to create your voice recording. So you should have both of these in by 6:30 p.m., 12 minutes from now in a week. Okay, any questions about this? Is the quiz descriptive? In multiple choice? No multiple choice. Yeah, go ahead, Luis.
I'm just wondering, what should we record? What should we include in the voice recording? Like that had been explained. So, but I just could you please
Yeah.
explain
Of course,
a little bit more specifically.
Okay. So if you cheated, which will obviously not be the case, don't send a voice recording, okay? Because you cheat twice by cheating the voice recording, but you won't cheat. So what you're going to do is you're going to say, hi, my name is Louis, student number 123456789, etc. This is my quiz submission. I found the quiz easy, or I found it difficult. I found it okay, but question 5 was difficult, something like that. You can say if you want. The important bit is my statement, I only used my work. I only used the formula sheet and the scientific calculator. I did not communicate with anybody during the quiz. The quiz is my work. I followed the instructions. So it's a way to get a bit more of a verbal statement that you did not plagiarize. By the way, same for the homework.
Okay, I see it now. Thank you very much.
And then we stick it in a machine learning algorithm, and it knows from your voice. It can listen to trembles of the voice, and if you lie, we know. No, I'm joking. We don't have that yet, but we will. Other questions? Apart from answer sheet and theorem paper, can we use draft paper? Yes, of course. So use draft paper. Okay, a lot of lols. That's good. We like lols. All right, so that's a quiz. Here's a quiz for you. Yours will look similar. And you'll have a practice questions for the quiz with Aminat this Friday as well. So if you go to 2020 year, this is a quiz. And you also have the solutions, okay? This is, you'll see, that's the type of questions you'll get in the quiz. Not too difficult, okay? Only content slightly different, because you'll have more linear algebra. No, so people have not struggled with finish time in general. Try not to make the quiz time constraint. Okay, so it's not about time constraint. It's a checkpoint of the material. Okay, so most of the questions quite straightforward. Checkpoint in the material. So that's the notion of the quiz. It's not a yeah. So you could look at this quiz. You can also look at the previous years if you want. Go to the year before that. This is 2 years ago. Here was a quiz. Okay. You see here's A, here's B, A union B, that's easy. This one was a bit hard for a few people. Okay. Will chapter 3 be on the quiz? No, so not everything. So a lot of stuff I'm just teaching today and some won't. I'll summarize this at the end of today. So I suggest just let's learn now linearly, and then you'll get a summary of what to focus on specifically. Okay, and that summary, you'll get that summary tomorrow or later tonight after the course. All right, more questions? Let's get to business. Chapter 3, Unit 3, Foundations and Logic. Now, I'm going to go a bit faster through some things here. We won't do everything. Our purpose is to touch some things and then move on. So so I must say, I mean, I think the notes we have here are kind of a bit too detailed for the level in which we're going. So we've already spoken about proof, and proof is showing that a mathematical statement holds. And what you'll see in this chapter is a lot of things that are kind of have to do with number theory, because some of the proofs kind of to understand the concept of a proof, it's good to speak about number theory. Well, basic number theory, right? So evens, odds, primes, composites. So number is prime if it's divisible only if it's greater than 1, and it's only divisible by itself or 1. Okay, so we're not going into this in depth. I'll stop a bit more on induction, because that is something we'll actually do thoroughly. Okay. Now, some things in terms of notation, this for all, I think I've already said, that means this is a quantifier which says for all x and d, the statement, this is a statement, this is like P of x. It's a statement about x. If P of x means P of x is holds, then Q of x is holds. Okay, that's kind of the type of this is if you're really formalizing proofs. But I'm actually just going to move on. There's an example here of what's not a proof. So let's see. So consider the statement that the product of any two odd integers is an odd integer. Okay, before we look at the not a proof, let's actually this is an invalid proof. We'll see why this is not a, well, it's not a correct proof. Not a correct proof is not a proof. Okay, but let's just see why the product of two odd integers is an odd integer. So does somebody have just a way of well, how would I see that? So two odds, 3 times 5 is 15. Or 7 times 3 is 21. You can't multiply two odds and get an even, so you get an odd. Why is that? Just my chat has disappeared. Sorry. Don't know how to. One sec. Okay, so now I see the chat again. Okay, so the odd numbers, let's call O now the set of odds, are all of the numbers of the form 2k plus 1, where k is an integer. Okay, so let me actually add another page here. So the odds are all of the 2k plus 1, where k is an integer. Now the claim is if, let's call this m and n are in the odds, okay, then mn is in the odds, right? That's a claim. So let's prove it. Proof. Okay, so if mn in the odds, that means that m equals 2k plus 2k1, let's call it 2k1 plus 1. And n equals 2k2 plus 1, where k1 and k2 are integers. Okay, because that's what being odd means. Being odd means that there exists some integer such that twice that integer plus 1 is going to give you that odd number. Once we've done this, we can just say that mn is 2k1 plus 1 times 2k2 plus 1. And now we can just do some algebra, and we can do, say, like that, and that's going to be 4k1, k2, and we'll do plus that, I don't know, 2k1 plus 2k2, do that one, and plus 1. Okay. So I think what we can do is now we could pull out a 2, for example. That's 2 times 2k1, k2 plus k1 plus k2 plus 1. So if you give me any two odds, I'll say, well, these are the two odds you gave me. So they have these two integers that are kind of their summary numbers. So they're the ones that define according to this. And then when I multiply, I've got this guy here. Is this guy an integer? Is 2k1 times k2 plus k1 plus k2 an integer? Yep. So, this thing is an element of the integers. Hence, m times n is an element of the odd numbers. You see, because it's twice times that integer plus 1. Yeah, so that's like one way of proving it. That's a standard way. Okay, let's see. Yeah, questions? Is that okay? So let's see what's not. And by the way, so okay, exercise. Prove n squared even if and only if n even. We used that last week when we spoke about the proof that square root of 2 is irrational. Okay, it's kind of in the same vein. And you can also prove other things, that the product of two evens is evens, etc. What's the product of an even and an odd? Even, yeah, okay. All right, so good. So let's see the non-proof. So this is the non-proof. Suppose that m and n are odd integers. If mn is odd, then it means that mn is 2k plus 1 for some integer k, right? I mean, that's what we kind of said about odd. So by the definition of odd, m is 2a plus 1 because we said they're odd, and n is 2b plus 1. Okay, here they then use k1 and k2, they used a and b. For some integers, a and b. Thus, if we multiply that, we get this thing, okay, which is odd. But the thing is, it's not a proof because well, because we're actually we're well, it's just not correct. So mn if mn is odd, we assumed mn is odd. It's almost too trivially wrong. So we said, hey, we're assuming m times n is odd, but we wanted to show it's odd. I hope that didn't confuse you. I mean, it's a wrong example, so this is not a proof, so it's bad. Okay. All right. In general, how to format a proof? You're not going to do too much proving, and with the exception of potentially induction, there won't be something you'll need to do. So there's not, but you just want a sequence of logical steps, and we don't have to be too picky about it in this course. Okay. So I'm gonna move through a lot of these things, and we'll get back to them if needed. So all of these have to do mostly with number theory, base elementary number theory, and we're not going to speak about that much. Something that you can't go without speaking about is unique factorization for integers. So when you have any integer greater than 1, then you can always represent it as in this way, as a product of prime factors. Okay. So, you can do like 24 is 2 to the power 3 times 3, for example, to the power 1. Okay, so you had 2 prime factors, and this one appeared 3 times, etc. And you can do this for any integer. So that's kind of an important basic property that you need. Okay. We'll skip. 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 So this is, yep. We'll skip up to here. Okay, so we'll do the rest with skipping all of that. So I'm actually I'll just note this so you have it in the GitHub. I mean, I upload these scribbles to the skip. We'll just get to quantified statements informally. So section 3.3, indirect arguments. So when you speak about methods of proof, the method of proof we did here was in a sense a direct argument. So it's It's not kind of one specific question. So we wanted to prove this claim or theorem or lemma or proposition. If these two numbers are odd, then their product is odd, okay? And we just used the properties of things and got to the conclusion. But there's also indirect arguments. So you've already seen an indirect argument last week when we proved that the square root of 2 is irrational. And I spoke about another one today when I spoke about Cantor's proof that the set of all sequences of zeros and ones, infinite sequences of zeros and one, is uncountable. The question is why there's so much to skip, because I think we just put a bit too much there. You're welcome to read it, but this course kind of sticks 2.5 courses in one. It's just a matter of timing as well. So since last year, we've been putting a bit more on the applications, even though we haven't had one in the last 2 weeks. I hope that we get to the set cover problem today. So we do a bit more applications and just a bit less of these things. All right, so in indirect arguments, there are kind of basically two basic things, and they mean different things. And let's see what they mean. So the contradiction and contraposition. Okay, so what is contradiction? The proof by contradiction. So what you want to do is you want to speak about the statement. So now I'm using the stuff we skipped, but I'm just going to say it quickly. So you see, this statement that I have in blue is read as, for all x in the set of things, the cases that we want to prove on, for all x, basically, you don't worry about this d, for example. It's just for all x, okay? For all x. If something holds for x, then another thing holds an x, okay? So, you know, for all living human beings have a pumping heart. Oh, I don't know if that's the right thing to say. I said I'm on the verge of a heart attack, perhaps, but I think it passed, by the way. So we're in the clear. Okay, so all living human beings have a pumping heart. Okay, so that's if I am a human being. This D is like I'm a human being, a living human being. Then, or well, for all human beings, you could say if I'm alive, then heart working. I mean, there's edge cases, etc., but let's not worry about that. Okay, so the opposite of that is that there exists a human that is alive and tilde qx. So this thing is negation. This is not. Okay, this is not. I think in the language R, for example, that's even how you do not, right? This not. Okay, some people do an exclamation mark for not, but okay. So the opposite of if I'm a human being and I'm alive, then my heart is working is there. Well, sorry, if there is a human being and she or he or they are alive, then their heart is working. The opposite is there exists a human being such that they are alive and their heart is not working. Okay. So this is the opposite of a statement. Okay. Now, to prove a contradiction, then you want to show that this assumption that this type of thing would lead to a contradiction, and that would bring you to conclude that the statement that you want to prove is true. Okay, so it's kind of a very formalistic way to speak about it, and we're not getting into it so much in this course, but the whole point is, you know, you saw the proof, for example, that square root of 2 last week is not a rational number, meaning there is not an m divided by n with no common factor, so it would be square root of 2. So the way we prove that is we assume there is and got to a contradiction. Okay, so that's proof by contradiction, and we might see an example, another simpler example below. Now, a slightly different type of thing that's sometimes confused is called contraposition. Okay, so contraposition is an equivalence between two types of statements, and I'll show. So you've got the this yellow statement here says, for all, I'll just again use an example, for all human beings, if alive, then heart is pumping. Okay, this yellow statement is equivalent to this orange statement, which says, for all human beings, if heart is not pumping, then not alive. Okay, so A implies B is not B implies A, but it implies that if not A, then not B. If not B, then not A. Okay, so these two statements, this one, which is like this, and this one, which is like that, or that, are equivalent. Okay, so sometimes instead of proving this, we find it more convenient to prove this. Okay, by the way, A implies B, one of the biggest mistakes that people make is that A implies B, they think that this thing implies that B implies A. But no. If I'm a man, I'm a human. That's A implies B. It doesn't mean that if I'm a human, I'm a man, because I can be of the non-male gender. Okay, that's it. All right, so let's see which example we look. No, we won't look at these examples. We'll get to concrete things of contraposition and contradiction later on. But at this point, you're just introduced to these two phrases. Okay, so in our world of proofs, we've got contradiction, contraposition. We've got a direct proof, and now let's slow down a notch and spend a bit of time on mathematical induction. Okay, so mathematical induction is a tool for proving things, especially when we have sequences. Okay, now it's actually a statement about sequences. Okay, so that's what you do. So the way you work with mathematical induction is, when you see statements such as this, or this is a statement about the real numbers. Now this appeared in your homework, right? You weren't supposed to. I think the homework had a K or something, but that of course doesn't matter. You weren't supposed to prove it in the homework, but you were supposed to ask Mathematica to get the formula for the sum of the squares, right? And you're using it in the homework. Okay, so let's say you're walking in the street and you find a note that shows you this formula. You can use mathematical induction to prove this formula. Okay, mathematical induction for such formulas is actually not constructive, so you need somebody to kind of tell you what the formula is. But let's see how this notion works in general, and then look at an example. And you know what? We'll do this example, which is also in your homework. I mean, there's already we discussed this before. I mean, you wanted a proof, so yeah, we'll actually give the proof for that with mathematical induction. Okay. So mathematical induction is a statement about the integers, the positive integers. Okay. So let Pn, well, it's integers from some point onwards, but typically we take the positive integers. So Pn is going to be a statement for the integers n. Okay. And A is like some initial value, some fixed initial value. Okay, often it'll be 0 or 1, but it depends. It can be, the third one or the fifth one or something. So the idea of mathematical inductions is assume that at the start it's true. Okay, PA, A is again your 0 or your 1, it's true. And then assume that you can show, and this is where you need to work when you do mathematical induction, that if it was true for the kth integer, then it's true for the k plus first integer. Okay, so this is, I'm going to put here like the exclamation marks. This is where you need to actually do something typically in mathematical induction. You also need to do something here, but it's often quite simple. Okay, so when you're at this situation, if this is true, and then when you go from k to k plus 1, then the idea of mathematical induction is that once you've shown that, you've shown it for all integers. Okay, this is often called the basis. Okay, that's what's written here. And this here is called the inductive step. Now, in mathematical logic, people actually work hard to use more basic axioms of logic to show that mathematical induction, is actually a valid thing. But we're in a sense, even though it's a proof, we're actually doing it like engineers in a sense. So we're just using mathematical induction. Let me go back here because my notes are starting to act up there. And induction example. Okay. So claim sum k from 1 to n of k is n times n plus 1 over 2, like you need to do in the homework. Okay. By the way, this class is very silent. Have I lost you, or is it because I'm skipping too many things? Probably skipping too many things. Okay, I see one item. No, thank you. Here, nope. Cool. Exclamation mark. That's a good one. Yes, just speak with punctuation. All right, proof. So base, or let's actually write the statement. Let's write the statement. So the statement, let's call it P of n. Will just be a bit more formal. Yeah, nice punctuation there. P of n is the statement. Well, let's just, sorry, I'm moving. All of this is P of n. Okay, that's P of n. So proof, we use induction. This is often how you say it. We use induction. P of 1. What's the statement P of 1? The statement P of 1 is the sum of k going from 1 to 1 of k should equal 1 times 1 plus 1 over 2. Let's see, that in my world is 1, and that in my world is 1 times 2 over 2, which is also 1. Hence, and that equals, hence, P of 1 holds. Okay, so we've just shown that P of 1 holds. Now is a step. Okay, this was a base, and this is a step. Now, assume P of k holds. Okay, what does it mean that P of k holds? It means that some, well, let me not use a k, sorry, P of n. P of n holds. It means that sum of k1 to n of k is n times n plus 1 over 2. That's what P of n holds means. Okay? Assume that holds. Okay. Want to prove P of n plus 1. We want to prove P of n plus 1. So what is the statement P of n plus 1? What is a statement? So try to say it just in words, or it's hard maybe to write the sum, but the statement P of n plus 1, I'll just write in brackets. So sometimes when you for n equals n plus 1 exactly. So that's, I'm not saying we've seen it, but we want to prove that k from 1 to n plus 1 of k is going to be, now look, it's going to be n plus 1 times n plus 1 over 2, right? So I've put for the n plus 1, exactly like case you wrote there. Okay, so that's what we want to prove. How do we prove it? How do we prove it? So what we're going to do is so this is just I'm telling us what I want to prove. Okay, how do we prove it? Well, we'll write sum of k from 1 to n plus 1 of k. And in all these summation proofs are actually very boring, and it's kind of not the way to do it, but that's to prove. You can do this, by the way. This is valid as a solution for your homework, but it's not the greatest thing in the world. I'm saying induction has appeared for better things than these summations. After this preamble of apology, what I want to say is I've taken the sum here that has n plus 1 terms, and I've broken it to the first n terms plus the additional n plus first term. Okay, see what I've done? I've broken it into that. Now this thing equals, okay, so here was the, let's call it the break the sum trick. Break the sum trick. This is just commentary, it's not part of the proof. To break the sum trick. All right, now what's our induction hypothesis? What does it say about this? The induction hypothesis was that Pn holds. So according, let's put here a bit of color, let's say, according to P of n, the induction hypothesis says that this is already n times n plus 1 over 2. Right, that was the induction hypothesis. And we want to show that it's plus, well, and that, so this is still coming from the induction hypothesis. At this point, what we can do is we can do some algebra. Maybe we, I don't know, multiply this by 2 and divide by 2, for example. Okay, and then you can factor out the n plus 1 and do an n plus 1 times n plus 2. Right, because this is an n and this is a 2. That's stayed over 2. Right, which is Pn plus 1. Okay, that's this guy. And that's it. That's the end of the proof. Then you put a square and you go and you have a beer and you're happy. Or something of some beverage that might have an influence on you. So you see, what you're doing is you've proved it just for the base. And then you said, if I know it for n, I know it for n plus 1. So then kind of everybody did that, and you know, some higher power did it for you and went from 1 to 2, and from 2 to 3, and from 3 to 4, and from 4 to 5. So that has proved it for all integers, and that's a proof. Okay. Questions about that? So that's the most boring, simple proof by induction example. And that should take us into our second break. Casey's not a beer guy. Neither am I, Casey. Okay, so I'll see you guys in a few minutes, and we could try and start in 700 or 500 in China, or 3:30, not 00 in India, I think. Anyway, in 7 minutes. See you. So that's that's an answer to 2B. By the way, a very nerdish answer. Much nicer answers were the other ones. Okay, see you in 7 minutes. Bye. All right, more questions. Hints from HC. Hints for HC. Sure. Why not? We live once. Sorry, I'm very with this dark humor today. But I really wasn't feeling good. Now feeling much better. All right. HC. Oh, yeah. So, look, I mean, when you are playing Monopoly, you have two dice, right? And you don't know which is, you don't care. You just, I mean, one thing you just care about is just counting the sum, right? But look now at how many times you'll get a 2 and how many times you'll get a 3. Or sorry, what I want to say, here are some possible outcomes. You've got 2 and 3, and 2 and 2, and 2 and 5, and 6 and 2. But 6 and 2 is like 2 and 6. Okay, so it falls within the same paradigm. And that's pretty much the hint. So yeah. Yeah, sure. Let's do 8 again with low numbers. There's a question for online quiz. We're supposed to handwrite the answer. Yeah, you take the photo, maybe paste it in Word and make a PDF or something like that, right? You can typeset, but I think most people, if you try to typeset the answers, that's bad. In such a short time, that's probably bad. So strongly recommend against typesetting. Using one of these electronic pens like I'm doing, maybe okay. All right. And there was a question to go back to, let's do that a second. So let's go back to combinatorics just for a second. So balls into bins again. Okay. N bins. N bins. K balls. Are 4 cases, and we're speaking about this one, n minus 1 plus k over k. By the way, n minus 1 plus k over k, how else can we, what's a different way to write that? This is identical. Say again, sorry?
We can't see your screen.
Oh, I'm sorry.
Sorry about
that. Yeah, thanks. Thank you, good you told me. No, oh, okay. I don't know why it had a bit of an issue, but okay, we're back in balls into bins. N bins, K balls, identical or unique are the balls, and limit of 1 or unlimited. We've used different words for that. And what Neil asked is that we see just another example for this, n minus 1 plus k over k. What's a different way to write this? Right, so you could have done n minus 1 plus k over n minus 1, for example, right? It's the same. Remember, I mean, because you can, here you're choosing the balls, and here you're choosing the separators. Choosing who is the balls is just like choosing who's the separators, because if they're not balls, they're going to be separators. All right. Now, a small example. Let's just do the monopoly example. So in a monopoly example, it's okay. It's in your question, but that's not the end of the world. In the monopoly example, you've got bins, which are, here are the bins. The bins are 1, 2, 3, 4, 5, and 6. And when I throw a die and I get a number 1 to 6, it's basically like taking the ball and putting it here, or he, well, or, you know, or I don't know why this is not working, but or here, or here, or here, or here, or here, right? And that would be the first die. So, and then the second die, you know, can also be here. It can also be in one of those 6 places. Okay, so any configure, like if you see it one like that, that means that the die had, you know, a die with a 1, you know, and a die with a 6. This is like a monopoly die, you know. The die is the cube you throw. You have to get the numbers. All right. So for the monopoly example, n equals 6 and k equals 2. I think it should give us 21. Let's see. So 6 minus 1 plus 2 over 2. What's that? 6 minus 1 is 5 plus 2, so 7 on 2. So that's 7 on 2 is 7 times 6. Well, let's just do it fully. Sorry. 7 factorial. 7 factorial divided by 7 minus 2 factorial. 2 factorial. So that's 7 times 5. What am I doing? Yeah, 7 times 6 divided by 2. And that's 7 times 3, which is 21. Okay. So there's 21 possible ways of saying what you got in Monopoly. I'm not talking about the sum. For the sum, you only have, you know, 2 to 12, like 11 ways. But I'm talking about configurations. All right. And that's actually your question 8, the last one. Yeah, you can consider this as 7 choose 2, but there's not a combinatorial meaning. I mean, the thing is it's this situation. I mean, yeah, it's equal to 7 choose 2. Now, if we're back onto this, to balls and to bins, let's just speak about sampling for a second. Okay. I mean, you guys are doing a Masters of Data Science, almost all of you. No, okay. So in the monopoly case, you got here, you've got 36 outcomes. So there's a question about 36. You have here 36 outcomes. When would you have 36 outcomes? You have 36 outcomes if one die is red, for example, and the other is blue. Is green, sorry, different, right? So that would be 36 outcomes. So 36 outcomes would be if you know, if one is a green one and one is a red one, then it's 36 outcomes. But if they're unique, but the dies are not unique, unless you mix 2 monopoly sets, and then they're kind of different. Dies are the same. All right. Now, this relates to the whole concept of sampling. Most of you are data scientists, almost all of you, master of data science. So when you're sampling, you can treat this balls into bins, which seems like a bit, I mean, who's throwing balls into bins? I haven't done it for a while, thrown ball into bins, but I do sampling quite a lot. Okay, and so we'll use data scientists. All right, so when you're sampling, there's kind of a different paradigm, which is not the balls into bins one, but it exactly matches it. So what do I mean sampling? So sampling is now there are 50 of you live and one of me, 50 of you on this Zoom chat. Okay, so there's a population of 50 of you. So population n equals 50. Okay, like 50 bins. All right. Now I can sample without replacement, and I can sample with replacement. Okay. Without and with replacement. What does that mean? What do I mean sample? So sample, I'm going to go to the list of participants, and I see now 50 names that are not my names, and I can take Zhao and Yukon and Yi and Lewis, for example. So that's 4 names, but I make sure that each time I sample a name, I don't put it back. Okay, so that's without replacement. Okay, so sample size is k. Okay, so k was 4 in this specific example. All right, now when I said those 4 names, sorry, I forgot the names, but let's say it was Kai and Julian and Lewis and Jared. Okay, it's 4 different names this time, but no big deal. Okay, so when I said these names, I can do it with order does not matter. I'm writing too many words here, but that's okay. And order matters. Okay, so again, I got 4 possibilities, just like the balls and bins, and these things are going to match exactly the same. So order does not matter and order matters, right? So again, I'll say 4 names, Kai, Lewis, Julian, Jared. But if there's order matters, then I can do all 4 factorial, which is 24 permutations of these for order matters, or order does not matter. Now, it turns out that the sampling story is just like the bin story, the balls into bins. And in the world of sampling, it's with replacement, without replacement. Order does not matter. Order does matter. Okay, so if the order matters and it's with replacement, then I've got, for the first person I choose, I've got n choices, and second n, etc. So it's n to the power k, just the same. Oh, and it'll be just the same here. And it'll be just the same here. And it'll be just the same here. Okay, so by you asking me, you reminded me to tell you of the mapping between balls into bins, which sounds kind of very technical, and sampling, which sounds more data scientific, and the number of samples you get is here. And the most common case is, again, this one. What is this case in sampling? What is this case in sampling? Sampling without replacement. So it's actually selecting a subset, and order does not matter. Okay, and if order with replacement is we put them back, it's going to be this one. Now, in the Monopoly game, you can say, you can do a different version of Monopoly game, and you can say, I've thrown a 6, say, afterwards you're not allowed to get a 6, so I'll throw the second die, but if I get a 6 again, I need to throw again, right? And that's like with, that would be like this case, sorry, without replacement. Okay, I think I've blabbered on enough about this. Let's get back to our induction. So, am I looking at the right thing? No, week 4. Okay, so we did one induction proof. So practice for quiz, or practice. Again, not all the material will be here, but in induction possibly is. So practice for quiz, this one. Okay, so it's the same idea. And by the way, you can go to the quiz of last year. So if you go now to 2020 course, this is 2020 course, and you go quiz 1. And I think we had a question like that, did we? No, we had a different question. Okay. It was this one. Okay, so I think in the year before that, that's a 2019 course 2 years ago on quiz 1. Yeah, that was like a question. But this is one of the things, you know, so again, it's just a bit of algebra. Once you know the formula, you need to follow the induction principle. All right, let us move on. That's mathematical induction. And yes, now logic. I'm going to run through this, and this will not be quizable, and it's not. It might be in the second assignment, but no. But if so, then lightly. So the most important thing here is just to see a bit of notation and just know that this thing exists. Okay, so mathematical logic in general. Okay, I mean all mathematical logical, but when we're speaking about logic, we're speaking about these variables which are effectively like booleans. Okay, so this variable p can be a boolean. A boolean variable is true or false, 0 or 1. Okay, so this is a true or false, and then you can do operations on these variables. So you see, and what we're going to do is we're just going to fill these out, and we'll make sense of it all. So if the variable p, and p can be sometimes a statement like, hey, something holds, it is dark or not, etc. So the variable p is true. This thing means not p. Okay, not p. So if p is true, what is not p? False. And if p is false, what is not p? True. Okay, so this thing is called the truth table. It's a way of, it's like a mapping from the variable to its not. That was kind of a bit too simple. But then we have this thing. And this thing is called sometimes a conjunction. And that's just a fancy word for and. Yeah, conjunction or and. And what does it look like in set theory? It's not sets here, but what does it look like in set theory? An intersection, right? It's just a bit sharper. Okay, and you know, an intersection, if an element is in the intersection of two sets, and then it's in an element of the first set, element of the second set, is where this comes from. So let's see. So this truth table gets as inputs two things, and the output, let's make the output green here. Okay, that's the output. So let's fill out the truth table. If P is true and Q is true, what's P and Q? All right. Next one, what's true and false? P is true and Q is false. What's P and Q? False, 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 false. That's lovely. What about a false and a true? What do we get? False. Two falses? False. Okay, so that's a truth table for and. And now we get to kind of the complementary guy. It's kind of fun. So fun that it's fun. All right. So that's an or. Okay. What does this look like in set theory? Kind of the opposite of and. Union. Right? So if an element is in the union of two sets, it's in the element of that or in the other one. Now, careful. In language, you can ask me, do I want a pizza or sushi? What were you asking me? You were asking me, do I want this or that? But probably not both, right? I mean, if you guys have me ever for dinner and you know, oh, I was your teacher in MATH7501, you suffered as, and you tell me, do you want a pizza or sushi? And you know, I'll tell you, I want both. You'll say, oh, what a rude teacher. right? I mean, it's not both, okay? But in logical OR, it can be both, okay? You won't want either, Casey. Okay, fair enough. All right, so P is true and Q is true. What is P or Q? True. P is true, but Q is false. What do we get? True. That's so fun. P is false, and this is, and Q is true. We get it true. What about two falses? Right. So the only way that the AND can be a true is if they're both true, right? This is kind of a very restrictive. And the only one that the OR can be a false is if they're both false. Okay, great. Now we can have some fun. We can now do, maybe this should be on the quiz. It's so easy, it should be on the quiz. I mean, in this specific form. Let's see. So now we can do some combinations, okay? We can do some combinations. So this is two different statements. This is this one, and this is, there's yellow are inputs. This green is one statement, and the orange is a different statement. It's fun discoloring it. Okay, so let's see. P is true and Q is true. What is P and not Q? This is P and not Q. False, 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 I agree. P is true and Q is false. What is P and not Q? True, 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 true. P is true. Yep, true. I agree. P is false. You can already stop here. Now, by the way, who knows? There are some, there are at least I know one, but there's several professional software developers here. If you're doing, what is short circuit evaluation? Who's heard in software development of short circuit evaluation? Well, in some languages. Short circuit evaluation. Somebody? No? Somebody developed in C. In Julia, it's that way as well. Short circuit evaluation. So when you're in some languages, when you actually have a logical statement like this inside the language, right? And this is going to be a condition, and this is going to be a condition. And this one was already false. Okay, I'm going to draw this red. It's already false. You know, so if this is false, because this is a conjunction, because this is an and, the whole thing's going to be false. In some languages, this will actually never be tested. Okay, this is never tested, and that's called short circuit evaluation. And you know, maybe it doesn't matter, but maybe this has an effect on the system, and it does. Okay, so, and similarly on the OR, if this is true, then whatever you have here will never be tested. That's a language thing, not a logic thing, but maybe some of you would have heard about it. Okay, so basically, having said that, what do we have here? What do we have here in this point? False. Okay, and the last one is clearly false. Now let's go to the second logical statement. Second logical statement. So let's see, P is true and Q is true. So we have P or Q and not Q. What is this thing? False. You see it's false. Okay, P is true and Q is false. So we have here a, what is this thing? This thing that I'm circling now should be a true, and this should be also a and with a true. So what's the whole thing? True. You see this. Okay. P is false and Q is true. This thing is still going to be true because it's an OR. Okay, and a, what do we have? Everything false. Good. And a false and a false is going to give us a false. Now, you see, these two statements, false, false, true, true, false, 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 false. So that means that this can be replaced by that. They're logically equivalent. Okay, that's what when two logical statements are the same. Yeah, if you had a computer program that had this condition, you could have had this condition instead. Okay. One such example of logical equivalence, which you've already seen in the notion in the world of sets, is De Morgan's law. Right? And you could try this in a computer program, by the way. So you can say, if not P and Q, it's the same as not P or not Q. Or the alternative form, if not P or Q, it's not P and not Q. Okay. Right. So De Morgan's appears there's De Morgan's for sets and De Morgan's for logical statements, and they're the same idea. So the not, what's a not in sets? What's a not in set? No, it's the same Morgans. Same Morgan, different context. That would have been interesting. And maybe there's a planet in the universe where two people named De Morgan invented these things separately, but it's the same thing in many ways. You could think about it a bit more. What's not in sets? Not if something is, yeah, I see a little C. That's nice. If something is not in the set A, it is in the set of a complement of A. Okay, so there are relations between these things. We're not getting into the all philosophical relations, but logic and sets are very related. Okay, a tautology always takes true. Okay, so for example, a tautology, if your compiler on a computer program sees you do something like this, yeah, let's see that this is a tautology first. So let's check. True and true, what does this give us? First statement, what do we get for true and true? Plug in here, true and true. What do you get? I see many falses, and that's false. What's true and true? So P, why do I get falses? That's it. Have you guys given up on logic? So true or true is true. And, not, sorry, that's not a tautology. I see. And not true is false. I fully agree. I've given up on logic. Okay, I'm to blame. Mistake with me. Sorry. Okay, so I thought this will be a tautology. It's not. So, so statement that's a tautology. Let's make a tautology ourselves. Okay, let's make a tautology. I thought this will be so PQ. And the true, 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 false, false, true, false, false. Of course, if you had more inputs, you'll have more combinations. So let's do P or Q. What's a tautology? No, let's do this. Here, P and not Q, or not P and Q. I hope I've made a tautology. Let's see. Let's see. I mean, if not, I can add one more. Oh no, okay. Or, sorry, I may is this, or P and Q. Sorry, I'm making a mess here. Does anybody have a good tautology to give me? So I want a statement that will always be true. Okay, come on, let's just go for the simple one. P or not P. Okay, let's just stick with it. Oh, and Trove's telling us the next table is, so thanks. But let's just stick with that because with this. So okay. So tautology here, P or not P. Okay, true gives us true false gives us true and a true and a true. So this is tautology. So if you have a computer program that has if condition this holds, then there should never be a branch to the else. There's never be something else. It's always going to be this guy. Okay, and you're saying this is a tautology, so this is too complicated for me to do now. I'll do practice check if tautology. Okay, thanks. All right. Then there's some more properties, commutativity, associativity. We're not going to speak about these too much. Well, not at all, because we're just going through this rather quickly. But I want to spend just a second on this one thing, which is the slight statement in this world of logic that's maybe not as intuitive as the and the or. Okay, and you should just know about it. So this one's called the if P then Q. Okay, I mean we've used this all the time. We did, if P then Q. Okay, or P implies Q. Okay, now this is now what I'm filling in is actually the definition of what it is. Okay, so and let's see that the definition would make sense to you. So if I get a true and a true, this is this first case. All right, so does true implies true? Yeah, so yes. Okay, now I got from one have the full answer. Let's see. Okay, and does true imply false? So if I put T imply false. No, because if some, that's the if my statement is if P then Q, then if I have a true, you can't have a false. But what about these two cases? These are the ones that are slightly more interesting. What if we had falses now? I told you if P then Q, and I'm telling you P doesn't hold. So you say all T? Yes. Okay, so these are the two cases that are a bit more out there. Sorry, that's wrong. I just made a mistake. So if I am if I'm false, then and this is true, then that's fine because with this being false, well, that's just how it's defined. With this one being false, then and this one being true, that's okay. But if I'm false and false, okay, that's also true. So the reason that this is, sorry, I'm mumbling and not speaking clearly. Let me just speak a bit more clearly. Sorry about that. So the reason that this thing holds is if the condition is false, then it can be that both the result is true or false, and they're both okay. So they're both true under this case. Okay. So let's just think. My statement is no. Okay. I'll leave an example, but I hope I didn't confuse it. But basically, this is a truth table for the conditional statement. Okay. So true implies true is clearly true for this conditional statement. True implies false is clearly false. But if we get false for the condition P, then we don't care true or false. So they're both going to hold. Okay. Now there's a claim here, and let's spend a minute on that as an exercise and see that P implies Q, that this condition is just like saying not P or Q. Okay. So let's just see. So here on the left, I'm just going to put in what we specified here. Okay, so that's going to be the true, false, true, true. And on the right, let's just do the computation. Okay, so not true or Q, we've got a true for this one. Okay, second one, not true is false or false. That's going to be false because this or is on both falses. Oops, sorry, that's going to be false. The third one is going to be a true. And this last one is also going to be true. Okay, so basically to say that P implies Q is the same as saying either not P or Q. Okay, so that's one bit here, and this all notes that logic is maybe slightly not trivial, but that's it. Okay, I'm going to skip the rest, and let's see if next week we can speak about this automated reasoning application. But there's actually another application which I wanted to speak about before for Unit 3, which is a set cover problem. However, what I'm thinking of is to keep both of these applications for after the quiz. Okay, so after the quiz next week, typically you're kind of exhausted after the quiz, then we do the two applications, and to speak about applications prior to the quiz is less, sometimes you have less excitement for the applications because you're caring about the quiz. Okay, again, I'll specify an email message that's, well, a Blackboard message that says what you need to do in proofs and logic in this whole Unit 3. It's not going to be a whole lot. Are you ready to go to the next bit, Unit 4? True or false? Are you ready? No? Quiet on the line? True. I see some trues. Yep, good to go. I see a smiley. Okay. Smiley is always good. Well, only if it's coming from within. Not sure. Okay, I see some honesty as well. All right. The next unit, which is our last discrete math unit, is about relations and functions. Okay. So we're starting with a concept that you know already, and that is the Cartesian product. Okay, so we spoke about the Cartesian product before. Cartesian product is the set of all tuples. The Cartesian product A cross B is a set of all tuples. Yeah, tuple is these ordered pairs here, such that A is in A and B is in B. Okay, and now we have this new concept, which we call a binary relation. Okay, and it's denoted here R. 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 Okay. And a binary relation is nothing but a subset of this Cartesian product. Okay, it's just a subset of this. I mean, this is like a very, very basic definition. Okay, so let's just see an example. Okay, this also serves as a bit of a review for the quiz. All right. By the way, the quiz also, of course, has linear algebra and things like that, and similar to the assignment. All right, so let's take the set A to be 1, 2, and the set B to be the elements A, B, C. So A cross B is the set of tuples 1A, 1B, 1C, comma, 2A, comma, 2B, 2C. Okay, that's what we have. Old friend, Cartesian product. Okay. So a relation is a subset. Take R now to be a subset of A cross B. For example, here is one specific R. R, well, of course, I can choose an empty set. That's going to be a bit boring, but I'll choose R to be 1A, comma 2B. Okay, that's what a relation is. That's what, well, a binary relation is a subset of AB. Okay, now, the way I read this relation is I'm going to, so that's all. That's the relation is, first of all, a subset. But the way I interpret it is it tells me that 1 is related to A and 2 is related to B. Okay, so the relation, and I can sometimes write this, I can write it as like 1 are A and 2 are B. Okay, that's a relation. Right, but it's just a subset of A and B. I could have treated this also. Let me steal another page and hope that buggy software will not be problematic. Okay, so I could have written the set A. I could have done A as A was my set 1, 2, 1, and 2, and B was a set A, B, C. And I could have drawn the relation as, like, you see, 1 is related to A, 2 is related to B. Okay, I mean, the other elements of the Cartesian product, I'll draw them in no, right, software has frozen. Sorry. The other elements of the Cartesian product, I'll draw them in yellow, which was this one, and this one, and this one, and this one. The other additional 4 elements, yeah, the ones that aren't these, right? The ones that are this one and this one and this one and this one, they weren't in this specific relation. So a relation is a subset of a Cartesian product, okay, which actually shows which 2 elements are related. Okay, that's what a relation is. All right. Let's do another example. So it seems like just a bunch of words, but it's actually relations. Functions are going to be special cases of relations. Where in data science does this type of relation also hold? In another course some of you might be doing with lectures tomorrow morning. Relations, relational databases. So when you look at the mathematics of relational databases, and you need to understand a bit of relations mathematically, at least. All right, so take the set A to be 0, 2, 4 and the set B to be 1, 2, 3, 4. So what is A cross B? Oh, it's a bit of a tiring thing to write, but let's write it. So we've got 0, 1, 0, 2, 0, 3, 0, 4, 2, 1, 2, 2, 2, 3, 2, 4, 4, 1, 4, 2, 4, 3, 4, 4. Now, here is a relation that's not going to be defined as a subset by actually saying exactly which elements. Well, it's going to say, well, it's the elements where x is less than y. Okay, so then you can say, well, let's actually write this relation first. Let's not answer this yet. Let's not answer this, but actually write the relation of all of the elements where x is less than y, right? Where the first element of the tuple is less than the second one. Let's actually paint them. X is less than y, 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 x, well, less than or equal. Less than or equal to y, less or equal to y. That 2, 3 is not in the relation. Am I correct? Yeah. 2, 3 is, oh yeah. No, sorry, I made a mistake. I mean, is the chat died? Okay, so nobody caught me on this mistake. So is this guy in the relation? Is this guy in a relation? No, so I made a mistake. This guy is not in a relation. Let's continue to paint who's in a relation. X less than or equal to y, x less than or equal to y, x less than y. This guy not in the relation. This guy not in the relation. This guy not in the relation. And this guy in the relation. Okay, so the relation is all the yellow guys. Okay, and I want to copy them just to save time, but they're all the yellow guys. These are the ones in the relation. Okay. And of course, 0R2 is, now when you say this thing which is now highlighted here, it's just like saying 0, 2 is an element of the relation. Okay, and 2, 4 is an element of the relation, and they're an element of the relation because for them x is less than y. Okay. Let's see what they want us to complete here. Since 2 is less than 3 and 2 is an A, 3 is an B, we have 2R3. Good. 2R3 is this guy. That's this. And here is the set of the relation, all of the yellows. Okay. All right. So that's what a relation is, not so complicated. It's a subset. That's what a binary relation is. It's a subset of the Cartesian product. Okay. And there's quite a lot here, but we're now going to move immediately to one of the most important concepts of mathematics, for which we have 6 minutes left, but that's okay. It's a concept you've already known, but now you're visiting it from the context of relations. Now, before I do that, I'm just going to take this 1, 2, AB thing, and I'm going to draw an axis, and I'll call this the set A axis, and I'll call this the set B axis. Okay? Because, you know, you guys know kind of functions you might have drawn. You know, this is x, and this is a function f of x, right? So, but now we're in general sets. In this case, it's still a small, simple set. So A will have the elements 1 and 2. Okay, that's the elements of A. And B will have the elements, let's just call them, for example, A and B and C. Okay, the Cartesian product is all of these points, right? This and this and this and this and this and this. That is the Cartesian product, right? Because each of these points, for example, this point here is C, 2. No, sorry, is 2, C. All right. Now, a relation was, from these points, a choice of who is in the relation. So, you know, it could have been that it's like this. In our relation, we only had 1A and 2B. That was this very specific relation, right? This 1A, 2B. But this is one way of viewing relations. And this, by the way, here, the bottom right, is a different way of viewing relations. Now, the second way should be quite interesting for you, because now you can think about a function, for example. So let's not assume that A and B are just these two small finite sets. Let's take A and B, A to be the real numbers, and B to be the real numbers. Okay, so I could still draw them like this if you'd want, right? This is a set A, this is a set B. The Cartesian product A cross B is now not just this grid of 6 points, this is whole infinite dense, is everything. You know, A cross B is everything. Don't have enough ink to paint it all. Okay, so that's R squared, the Cartesian plane, right? A relation is just some subset of R squared, right? Now I could have taken, for example, this shape here and said that all these points here are some relation. Okay, but that's not a function. So the way you would think of a function visually, and you'll see that the function, the way we're going to find it from a set theoretic sense, is going to agree with that. A function, you maybe would say, oh, this is like a function, right? Okay, so this is like a function. Now, this function, you could think of it also as a relation if you'd like, because it's a subset of R squared. Okay, here, let me draw another relation and tell me if this is a function. Is this red thing a function? Is this red thing a function? No, because you know from other places in math that for one x here, I get two y's and I don't have a function, right? So this is not function. And this here is function. So let's now go to the definition of a function. A function, and you denote it like this. You often denote it like this. It's a function that takes elements in A's and gives you elements in B, but let's see what the definition is. For us is notation. Is a relation from the set A to B, which also has its following properties. For all the x in A, for any x in A, you need some y in B that's in the relation. Okay, I could have written this thing as x f y. Okay, according to the relation rules. So that means for any x in A, you have something in B. So if the function is defined over all of the reals, then for any real value, I get some element. At least I get an element. Further, for all x in A, and now take 2 points in B. Whoops, I didn't mean to do this error. That's impressive. For all x in A, and I take 2 points in B, if xy is in the relation and xz is in the relation, then y equals z. Okay, so that means that I cannot have, if I've got now the points x, let's put the points x, this is x, and this is y, and this here is z. Okay, so it says xy is in the relation because this is a point xy. And this is a point xz, right? Now, I must have that y will equal z, and that's not the case, and that's why this is not a function. So basically, it means that for an input, you only get a single output, okay? So relations that satisfy this, relations like this guy, are a function. Back to our original relation, and we finish. Was this thing a function? Was the relation R 1A 2B a function? Was the relation 1A 2B a function? Yeah, it was a function, right? If I would have added to the relation, is the relation R tilde 1A 2B 2C. Is this a function? No, not function. Not function. Okay, the thing that we haven't covered is speaking about when a function is one-to-one and onto and a few things of domain and stuff like that. We'll have to do that after the quiz. So you'll have a practical with Amina Friday that will prepare you more for the quiz. You'll get a note either tonight or tomorrow morning about the quiz content. And yeah, that's it. My consultation hour is tomorrow at 11 a.m. Brisbane time. I'm sorry that before I actually had the wrong Zoom link. I said it was on the class Zoom link, but go to Blackboard. You'll see an announcement. It's another Zoom link. Okay. All right. Have a good one, everybody, and thank you. Bye. Bye-bye. Ciao.